Okay. Well, good afternoon to everybody. It's a pleasure to welcome with the group from the Institute of Microelectronics and Microsystems, which is part of the Consiglio Nazionale delle Ricerche in Rome, Italy. Um, the visit of this delegation from the IMN, yeah, is because it's part of our international agreement. Yeah? It's a bilateral project. Yeah? This agreement it was signed between the CNR and CNPq in Brazil. Well, our speaker today is Dr. Valter Fuscaldo, who is a senior scientist at IMM. Yeah. And well, this is Walter's third visit. So now we consider him just as a member. Yes, as a yes, a dear friend, and also yeah, a part of our community. Okay, part of our lab. Well, I did today. Dr. Walter is going to present uh, this. Uh, it is results, no? Several results that are part of this collaboration, and the title is Metasurface Antennas for High Data Rate Sub-THz Wireless Indoor Communications. So the acronym of this title is Metasurfant. Metasurfant. Was surfacing, something like that. surfing in the meta surfaces. Okay, well, welcome, Dr. Walter, and please let's give a welcome applause. Yes. So the floor is all yours.
Muito obrigado. É a terceira vez que eu venho aqui, mas não consigo falar em português para apresentar. So forgive me, but the presentation will be in English. Maybe the fourth time, we'll see. Okay, so thank you, Hugo, for your kind introduction. As Hugo said, this presentation is about a project we are pursuing in the frame of a bilateral agreement between CNR and CNPq. The agreement was signed last year, 2025, but I was here even in 2022 and 2023 in the frame of a similar agreement between CNR and FAPESP. That time, Dimitris Zografopoulos, one of the members of this team, was the PI. Now I am the PI, and I am proud to present this project where we are trying to do, myself and my colleague Edoardo Negri, Francesco Maita, Luca Maiolo, and Dimitris, that unfortunately cannot be here, about the development of metasurfaces for realizing novel antenna devices for high data rate communication in the THz band. So let's see if it works. Yeah, that is not sliding somehow. Okay, let's see. Okay, now it works. So during this presentation, I will start with a brief description of the project, just to give an idea of the objectives that we have in these 2 years workflow. And then I will try to give you a broader presentation about the topics that we will cover under this project that relate to the design, analysis and design, say, of THz fiber per cavity leaky wave antennas. Actually, my first research field was related to leaky wave antennas, and now my main research axis in the THz. So I'm trying to combine these two research fields in this topic, and then I will give you a few more details about the topic of the project itself, that is the realization of a peculiar kind of metasurfaces that allow to obtain an enhancement of the gain bandwidth trade-off that typically affect such kind of radiators. And then I will show you some preliminary results that we have obtained in this first year of the project related to the characterization of such kind of metasurfaces in the THz range. So let's start first with a brief introduction about the context of the project, that is THz, and just let's try to give a rationale behind the decision to study antennas in the THz range. So for those who are not familiar with this frequency band, is commonly considered that part of the frequency spectrum that is sandwiched between microwave frequencies and optical frequencies. In the optical range, we have photonics technology. In the microwave range, we have the electronics technology. In the middle, we had a sort of THz gap because we lack some efficient sources and detectors, as we will see in the next slide. But an important improvement of this technology has been made in the last decades, and starting from the first niche applications in the astrochemistry field or in the security screening. Probably you know that not at THz, but in the sub-millimeter wave ranges, we already have some scanners that are working in the airports. Then we had a lot of application of the THz range in biomedicine, where they exploit the non-ionizing character, and so a safe character of this radiation, and considerably small wavelength to perform diagnosis of some kind of disease, such as skin cancer diagnosis and similar kind of disease. And this is also related to the application in the medical imaging, but the important application that have been opened by THz technology in the recent years is that related to indoor wireless communications. Why? Well, because as you may know, the most important figure of merit in wireless communications is the bandwidth. So as far as we need a large bandwidth, and most of antenna devices are limited in terms of fractional bandwidth, that is actually the figure of merit that limits the gain of antennas. The only option that we have in order to increase the bandwidth is to increase the operating frequency, and that is the reason why we are targeting THz frequency or sub-millimeter frequencies to increase the efficiency, the data rate of wireless communications. There are pros and cons in this. The disadvantages of targeting such high frequencies are, for sure, the free space path loss that increase a lot as you increase the frequency, and also the presence of water absorption lines in this frequency that can affect the range of the communication. So this is the reason why we used to talk about indoor wireless communications and not long range links when we targeting such high frequencies. So I mentioned that a THz gap in terms of technological solutions existed in this frequency range, but now this gap has been considerably narrowed, and indeed we have now a lot of sources and detectors available with a decent efficiency and power. Here you can see a list of them. Some are continuous wave sources based on quantum cascade lasers or photoconductive antennas or waveguides. And in terms of materials and systems, also we are now increasing the portfolio of materials that are suitable for high frequency application, because for instance, one of the aspects that limit the application of electromagnetic materials in the terahertz range is the loss tangent of common polymers that usually increases at high frequency, but there are some materials such as cycloolefin polymers that can replace the Teflon-like materials that are used at microwaves in terms of both refractive index and loss tangent, because they still have a quite loss tangent at such high frequencies. And also in terms of setups that we can use to measure the performance of devices, we are now equipped with spectroscopic setups based on the frequency domain and the time domain, in addition to the vector network analyzer that here you know very well because of the excellent facilities that here at FEC you now have based on the Andritsu network analyzer that can go up to 500 gigahertz. So if we want to call it terahertz, yes, it's terahertz. It's half of a terahertz, but it's still terahertz. So we will not talk about all these systems in this presentation, but we will see some hint of these two kind of sources, because these are the one that we can use at CNR in order to perform spectroscopic analysis. And we will mention waveguides because there are the sources that will be available here at FEC, and we hope can be used for the sake of this project. And then we will talk a little bit about the time domain spectroscopic system that we have and that we have used for doing the preliminary measurements of the metasurfaces that we are trying to study in the frame of this project. So this is just for giving you a context of the project. So now let's go to the objective of Metasurface. So we actually have one important goal, that is to design innovative metasurfaces to realize terahertz antennas that enable high data rate wireless communication. But this is an ambitious goal, and in order to reach this goal, we will have to address several other challenges or objectives. From a theoretical viewpoint, the first objective is to improve the antenna performance with innovative metasurfaces, because as you said, terahertz pose us with the challenge of having a good bandwidth, but with a high gain. And so this is kind of difficult with antenna solutions, because if you want to have a large bandwidth, you have to sacrifice something in terms of gain. And the first objective is to find if we can break somehow this trade-off. Then we have an objective is in terms of methods, because we need to develop new analytical and numerical solutions to study this structure. We will think about using waveguide and transmission line theory in a peculiar manner to aid full wave simulation to analyze such structure. The structures that we will study to break the gain bandwidth trade-off are called during this seminar TIC-PRS, where PRS stands for partially reflecting screen. It's just another way to call a metasurface, as we will see. Then we have a challenge in terms of the realization of these devices, because it's not as easy as in the microwave range, because the wavelength is increasing. If we want to design metasurfaces that are often characterized by sub-wavelength features, we need some precise nanomicrofabrication technique based on, for instance, in photolithography. And then we need to assemble the waveguide-based devices that will feed the antenna with the antenna itself. So we need some sort of expertise in this respect. Then we have the objective of testing these devices. So as concerns the characterization of metasurfaces, we are at a good point, because this is actually the main result that we have obtained so far. But then we have to actually measure the antenna pattern, and this requires VNA measurements, and this is probably one of the last objectives of the project that hopefully we will achieve at the end of of the project, so end of 2026. And as concerned the dissemination part and the transfers of knowledge, of course, the objective is to increase the mutual visits between us and to participate in other project calls, conferences, having good papers together. So the task force for this project is composed by myself, of course, and by the colleagues that I mentioned before, Luca and Francesco. Some of you already know because of the previous visits that we made here in 2022 and 2023. Dimitris, some of them have met in the previous visits, but this time couldn't unfortunately join. And Edoardo is the new entry that is actually the guy over his shoulders are carrying all the burden of this project, because he's the younger one, so he has to do things. We just need to present, you know. So the good point of this research team is that we have an expertise that is complementary among us and is relevant to the project, because mostly Edoardo and I perform the theoretical and numerical investigations of these metasurfaces, but without Luca and Francesco, we won't be able to make these ideas reality, because they are the ones who fabricate the antennas and give us a feedback to make this structure feasible. And we are actually seeking for the fabrication of the THz antenna in itself, because we are able to realize the radiating part, the metasurface, but we lack some expertise in realizing the antenna as a whole part with the waveguide feeder, its integration, and all the challenges that we will see during the presentation. Then we need somebody who is able to characterize the antenna pattern at THz frequencies, and also to test the link, to send the data over a THz link. So just I can go quite briefly on this aspect. This is the work plan of the project. So we are about at the end of the first year. We have 6 different work packages that goes from the theory to the experimental demonstration of the main components that are the metasurfaces, and then the experimental demonstration of the overall device, or of the overall link actually. So far we reached this point. Green rectangles represent the work package in which we have succeeded. The orange, yellow-orange one, the one we are working on, and the red ones, those that are still missing. So far we have made a successful comparison of conventional metasurfaces and the new one that we have thought as a possible solution for the problem, the challenge of having a high gain, large bandwidth device. And we are in the process of getting preliminary results on the whole system. So this is one of the purpose of this visit, was to understand what are the capabilities of the vector network analyzer. And yesterday with Cynthia and the other guys of the research team, we tried to figure out how we can go further in this process. And then of course we have several other objectives that we will push through during the second part of the project. So now let's go into the scientific aspect of the presentation. So I want just to give you an idea of the class of devices that we are targeting to during this process, during this project. And then I will go a little bit more into the details of the specific solution we have explored in this year. So I assume not many of you are familiar with Febbre per occhi vitilichi antennas, so they might appear as a complex system, but they can be thought as a quite simple system. Actually, in order to understand how a fabric perocavity leaky wave antenna, you can just think about the parallel plate waveguide that I assume you are all familiar with, where the top metallic screen is replaced by a partially reflecting screen for allowing radiation. So this is no longer a parallel plate waveguide, but is called the leaky parallel plate waveguide because power leaks out from this wave-guided region and starts to radiate. The important point of leaky wave antenna is that you have to, you cannot perform any kind of aperture on this metallic plate. You have to engineer the way you open the partial reflecting screen in order to get directive radiation in the point in which you want to radiate the electromagnetic energy. So the entire art of a fabric perocavity leaky wave antenna is in the engineering of this partially reflecting screen here. Of course, this structure radiates because you have when you feed it within the cavity with even a non-directive source as a dipole. So this dipole excites usually the first higher order mode of the parallel plate waveguide, that the T and TM higher order mode of the PPW, the parallel plate waveguide, that now are no longer guided modes, but are called leaky modes because the structure radiates and leak power out. So, as I said, if you engineer well the PRS, in practice, if it is highly reflective, the contribution to radiation by these leaky waves is the dominant one. And the maximum directivity at broadside in the vertical direction is achieved when the substrate is lambda over 2 thick. That is the reason why we call this also a fabric perocavity, because a fabric perocavity, as you know, is just a structure that has a resonance at lambda over 2. So this is a dispersion diagram. So basically you have the frequency on the horizontal axis and the phase and attenuation constant normalized to the wave number over the y-axis. So when you have this representation of the dispersion diagram, the curves of the parallel plate waveguide will appear as the one shown here with the yellow solid lines. When you open the structure, you will see that the leaky modes are quite similar to these parallel plate waveguide modes because the metallic, the PRS, the partially reflecting screen, is highly reflective, and so is a small perturbation of a metallic screen. And so they just slightly, the dispersion diagram of these modes just change a little bit with respect to the guided modes. So this dashed line represents the line where the wave number of the mode that is propagating is equal to the free space wave number. So that means that guided modes are below this line. That's, let's say, fast modes are below this line. Slow waves, surface wave, are above these lines. In order to radiate, you need a mode for being below this line because you need to associate an angle of radiation to the phase constant. So the phase constant is the normalized phase constant beta of the mode can be expressed as the sine of an angle, and the sine of this angle will give you a value comprised between 0 and 1 that is related to the angle of radiation of the structure. So in other words, you can think about a fabric perocavity leaky wave antenna as a middle of the way structure between a grounded electric slab, that is one that has no partially reflecting screen on top, and a parallel plate waveguide. So grounded electric slab possess surface waves only that has this behavior in the dispersion diagram, whereas parallel plate waveguides only possess guided modes that have this dispersion diagram. So leaky modes will appear actually in this region and will represent the radiation from such kind of structure. So the structure that we analyze in this in this presentation are actually possess an azimuthal symmetry, so they are just not a one-dimensional parallel plate waveguide, but they possess this two-dimensional representation, so they are actually two square metallic plates, one on top of the other. The one on the top, as I said, is only partially screening the cavity in order to allow for radiation. In this way, as I said, if the leaky modes, the no longer guided modes between this cavity, if the structure, the partially reflecting screen is highly reflective, they represent the dominant contribution of radiation to the total field radiated by the structure. And as you should know, probably, in order to obtain the radiation pattern from electromagnetic theory, you just need to perform a Fourier transform of the aperture distribution. As long as the dominant contribution of the aperture is a leaky mode, you can just use this simple expression to represent the aperture field of a leaky waves. And so you just need to do the Fourier transform of this simple aperture, where this wave number here is the wave number of the leaky mode, to obtain the radiation pattern. Since the aperture field is just an exponential term, its Fourier transform is a Lorentzian pattern that has a maximum when the phase constant has this value here, that is the angle of radiation of the structure. So if the phase constant is close to 0, it means that the maximum radiation will be at broadside, when the antenna has maximum radiation in the broadside direction, as represented here, and will have a pencil beam. And on the other hand, you will have a way higher directive beam when the attenuation constant is the smallest as possible. This means that the higher the reflectivity of the screen, the smaller will be the attenuation constant of this mode, and the higher will be the directivity of this structure. Why? That there is a simple explanation of this condition. If you think about Fourier transform, if the attenuation constant is very small, you have a sort of uniform aperture distribution, and so you have a cardinal sign function radiated. If you have an exponential term, an exponentially decaying term, you will no longer have a uniform aperture distribution, and the beam will start to spread out and lose directivity. So in order to have an antenna that shows a highly directive beam from such kind of structure, you need to make this partially reflective screen as much as reflective as possible. But as you said, as I said at the beginning, the larger the directivity, the smaller will be the fractional bandwidth. So we need to figure out a solution. How we analyze this structure? Well, we can, I can skip the mathematical details, but we can just establish a transmission line model between this stack of metallic and dielectric layers. So you have just a short transmission line segment ended with a ground plane with a shunt admittance that represent the partially reflecting screen. And then you have the infinite transmission line that represent the radiation to free space. With the analysis of this transmission line network, you can find the resonances of this network for both the T and the TM modes. You will find two expressions. By equating to 0 this dispersion equation, you will find the resonances, and you can actually find two kinds of resonances. The surface waves, as I said, that are the non-radiating modes, and the leaky modes, that are the one we are interested in, because they are the radiative one, because the normalized phase constant is smaller than 1. That means the phase constant is smaller of the free space wave number. So when we look at the dispersion curves of this structure, we can establish an easy connection between the dispersion diagram and the radiating properties of the structure. These are two examples of not quite, I mean, a quite reflective, partially reflecting screen that is characterized by this number. This is the sheet acceptance of the metasurfaces. And this is the dispersion diagram that you can find with that method. If you place your working frequency at this point where the phase constant and the attenuation constant are close to zero, the antenna radiates at broadside with a very sharp beam because the attenuation constant is quite small. When you decrease the reflectivity and you still go at the frequency where the phase and the attenuation constant cross each other, you still have a pencil beam, but as you can see, the beam width is increased, so the directivity is lowered. If you change the working point, you will increase the phase constant and the beam will start to point at a different direction, no longer at broadside. That is, for our purposes, an unwanted behavior, because we want the maximum directivity at broadside. We want the antenna to point just in front of it. So from this analysis, we understand that the design parameters that govern the radiating properties of the structure are the sub-THz thickness or the frequency. Actually, you have to change the electrical path between the resonances of the cavity to change the angle of radiation. And you can control mostly the directivity of the antenna by controlling this value here, that is the PRS acceptance. We will see that actually this works only when you consider a PRS that has certain peculiar properties. This is true when you assume that the leaky wave is dominant over your aperture field, but one may argue, okay, but what if the leaky wave field that you are talking about so far is not dominant on the aperture? Well, you can perform a full wave simulation and compare the results and see if the total pattern compares with your previous analysis. And indeed, for this structure that we have considered here, where the unit, here you see the partial reflecting string in this case, consists of a lattice of say, we call this unit self-fishnet because it's like a patch with strip gratings on top. Is a topologically connected metasurface that has very narrow gaps among each metallic pattern, so it's quite reflective. When you consider distraction, you analyze this with this simplified model, you get a pencil beam that is in perfect agreement with the one that you obtain if you simulate the structure on CST. The problem is that if you want to do this full wave simulation, these are lambda over 5 unit cells over an aperture that is about 20 or 30 lambda. So one of these full wave simulation takes you about 8-9 hours. With this transmission line-based analysis, you get the same results in probably 3 seconds, something like that. So that is the reason why it's better to understand how a leaky waves works instead of performing a brutal force simulation on CST. But we can do more. We can make approximation of the dispersion equation and get more insights on the physics of this kind of structure. Basically, if you study this dispersion equation in the limit of having small losses, that is for highly reflective metasurfaces, you find the relation between the pointing angle and the substrate thickness. That reveals that the thickness that maximizes radiation is related to the lambda over 2 condition of Fabry-Perot antennas and the radiation angle that you want. So you go back to the usual condition of Fabry-Perot antenna when you want your antenna to radiate at broadside, because the angle of radiation will be 0, and you will get that the maximum radiation will be reached when the thickness is about lambda over 2. Then you discover that the radiation efficiency depends on the length of the antenna, and you find out that if you want a radiation efficiency on 90%, that is usually a common value, you need to apply this formula here that tells you that the aperture length normalized to the wavelength is inversely proportional to the attenuation constant. This means that the lower is the attenuation constant, so the higher the gain you want to have your antenna, the larger has to be the antenna as well. Then you find other important physical insights if you study this dispersion equation under the hypothesis that the phase constant, the attenuation constant are almost equal to each other. In that case, this is the condition where the antenna radiates at broadside, and you find that the directivity and the fractional bandwidth are one proportional to the square of the sheet's acceptance, and one is inversely proportional to the sheet's acceptance. If you make the product between the directivity at broadside and the fractional bandwidth, you get a constant value that is 2.47 over epsilon r. This means that the higher figure of merit for a Febvre-Perot cavity liquid antenna is a constant that is maximum when the cavity is filled with air. But you cannot do anything to improve this value. So the larger the fractional bandwidth, the directivity will be the lower. So we have to figure out to resort a solution to break this trade-off. And this is called this can be obtained through the thick PRS I mentioned. So let's see how we can move from the traditional solution based on what we call thin PRS, thin partially reflecting screen, to thick PRS. So let's start from conventional metasurfaces. I have shown to you one of these realizations made by these efficient unit cells, but actually there exists a bunch of geometries to realize metasurfaces. The most well-known are the strip gratings, as you can see here, and the Babine complementary structure, the patches, the rectangular patches or the square patches. Why are so well known? Not only because they are simple, but because you have analytical formulas to characterize their sheet impedance. That is actually the design parameter that we need to understand which is the maximum directivity that you can get from an antenna based on the Febvre-Perot cavity principle. So what about arbitrary shapes? What if I don't want to use these guys and I want to use a different kind of metasurface? Well, it's quite simple. You can perform a full wave simulation in a unit cell environment. You can get the impedance matrix, the S parameters, whatever you want, and you can extract with a simple transmission line model the sheet impedance. But this is not helpful if we want to understand why a conventional metasurface has enforces this gain bandwidth limit in a Febvre-Perot cavity liquid antenna. If you want to understand why such kind of solutions enforce a limit in the gain bandwidth of an antenna, we have to look at the reflection coefficient of this PRS looking at upwards. That means that we have to look at the reflection coefficient of this structure when we excite the antenna from below. If we look at the reflection coefficient from this point, looking upwards from the source, and this is again a value that you can get from a full wave simulation. It's just a matter of changing the Floquet wave port, and looking at the S11, that is the reflection coefficient. A simple transmission analysis reveals that the phase of the upward reflection coefficient has this expression here. That is a quite simple one. When the structure is lossless, that means that shows a purely inductive or capacitive behavior. This sheet's acceptance goes as minus the inverse of the frequency, or either is proportional with the frequency. As a consequence, the phase of this simple PRS, the phase of the reflection coefficient of this simple structure, are always monotonic decreasing function of the frequency. And this is also a consequence of the more general forced reactance theorem. And you can say, what are the implications of this behavior of the phase constant? Well, if you apply simple ray optics analysis of the Febvre-Perot cavity liquid antenna, and you look at the power radiated at broadside in terms of the phase of the reflection coefficient, you get that the maximum power at broadside is obtained when this condition is fulfilled. Well, what does it say? It says that the phase of the reflection coefficient has to be equal to this combination of parameters that report also the wave number with along the vertical direction. Well, this is a monotonic, always increasing function of the frequency. So you have an always decreasing function and an always increasing function of the frequency. So they only met at a single frequency. And this enforces the narrow bandwidth behavior of this structure. So we need a pure S that shows a phase of the reflection coefficient that is non-fostered, that is not a monotonic decreasing function. That is the goal. And the first thing that we can do to break this behavior is to add losses somehow, because this relation holds only when we have a purely inductive or capacitive behavior. How we can introduce losses without affecting the gain of the antenna? We can introduce radiative losses by adding a dielectric layer, even a lossless dielectric layer, so a very low loss dielectric layer on top of this PRS. And this is why we call it a thick PRS, because it's a thin PRS with a thin dielectric cover on top. And this breaks this non-fostered behavior. And this is an example of this structure. This is a thick PRS now that should be realized by adding a dielectric cover of an appropriate thickness. And as you can see, the phase of the reflection coefficient is no longer monotonic, has this slope and this flex in its behavior. And as a consequence, an increase in, if we look at the phase of the vertical wave number, that would be an increasing function of the frequency and will meet the condition for maximum power at broadside in 3 points, and this will increase the bandwidth of the structure. What does it mean, appropriate? Well, appropriate, it means that it should be large enough to enforce a further resonance in its thickness. Here you can see how the modal field of this antenna, the leaky wave modal field, behaves when you have just a thin PRS, a normal partially reflecting screen. In this case, the modal field has a maximum almost in the middle plane, as usual for also parallel plate waveguides. If you add on top the electric layer, you will start to have some resonant behavior, but as you can see, it is not large enough, it's not thick enough, and you still not get resonance. But as far as you get an appropriate thickness of this dielectric layer, you start to see a resonance forming within this layer, this dielectric layer. And this is the condition that allows you to increase the bandwidth. So how much is this 1.3 millimeter? Is about lambda/4. So that is the thumb rule for having a large gain, large bandwidth structure with this kind of architecture. How did this study these systems? Eduardo did the magic. So it is true, Eduardo did the magic, but ChatGPT did the pick. I mean, so I should say what is the copyright of this picture. So how he did the magic? He applied the transverse resonance technique to this more complex system, and he was actually able, through this analytical transmission line approach, to find the condition for studying the dispersion diagram of this complex structure. Because before, when I show you the dispersion diagrams of the thin PRS, the dispersion equation was a quite simple one. It was on a single line. As you can see here, you have to make some additional math to get a fully analytical approach to study the dispersion diagram of the structure and understand when they can bring you to the gain bandwidth enhancement phenomenon. So we exploited his model, and we actually find that at the lambda/4 condition, the dispersion curves show this behavior. And what we see, that the phase constant that is represented with these lines is crossing with the attenuation constant no longer at a single point, but over a given bandwidth. And this explains why we are increasing the bandwidth of the structure. When we analyze the device that Eduardo studied analytically with full wave CST simulation, we found a perfect agreement between simulations and analytical results, and we actually obtained that the gain bandwidth figure on merit was as large as 4. And I remember that the larger value that can be obtained with a thin PRS is about 2.5, only when you are in when you use an air-filled cavity. Here we are in this condition, we almost doubled the gain bandwidth figure on merit, and this not even the optimum results that we have achieved so far. So this is just an example, but we can do even better. So actually this is the full wave simulation of the structure. We had to feed the cavity. So the first idea that came to our mind to feed the structure was to use a waveguide feed. But when we used only the waveguide feed, we didn't find a good impedance matching. So we had to consider two irises as a matching network within the waveguide. And I mean, when you start to design an irises in a full wave simulation and you perform parameter sweep, again, you can lose months before you get a good impedance matching. So we performed a sort of semi-analytical techniques that exploit one full wave simulation and different transmission line configurations in order to have a fast analysis of the structure, and we were actually able to have an impressive impedance matching with the structure. So this is the S11 when no irises are placed in the waveguide section, and this is the S11 after the irises are placed. So you see it dramatically improved. So now we have to figure out if we can do that at THz. We can, but it takes some efforts. For instance, if we think about having this structure fed through a slot in the ground plane, we can think about two ways to excite this structure. One can be done by using a photoconductive antenna, for instance, with a focusing lens to focus for not wasting too much power of the radiated power. The other one is by direct waveguide excitation, but in this case we have to figure out some flanges to assemble the waveguide to the structure. And also we have to figure out how to create the irises in the waveguide section in order to get a good impedance matching. Another possibility that we have exploited when we realized similar antennas when we work in collaboration with the University of Rennes is to use this back-to-back configuration where you exploit the non-directive radiation of a photoconductive antennas and you collect them with a waveguide horn that is back-to-back with the slotted Fabry-Perot cavity ligament antenna. And this is actually one configuration that works quite well. Now let's go mostly to the end of the presentation where I can show you the experimental results that we first obtained on the characterization of thin and thick PRS. So first, a brief introduction about how we can characterize this structure. We are actually equipped with a THz time domain spectrometer system. How does it work? Basically, THz radiation cannot be directly generated, or I mean, not at the low THz range. You always need the laser source and some transducer from the laser wavelength to the THz radiation. This sort of transducer is the photoconductive antenna. So you have a femtosecond laser, basically, that excites this photoconductive antenna. So you have these laser pulses that excite the photoconductive antennas. One laser pulse is forwarded to the transmitting antenna. The other one goes into this translational stage in order to have a sort of pump and probe analysis of the laser pulses. So you can reconstruct the pulse by changing the optical path of the laser by moving this translational stage. So this pulse is exciting the photoconductive antenna that emits in the THz range. This THz beam is sent to the sample and is collected back through the photoconductive receiving antenna. So the The other pulse that is sent to the translational state probe this THz beam and reconstruct the THz wave that has interacted with the sample by changing the position of this translational stage. So with the animation is easier to understand how it works. This probing beam is actually reconstructing the pulse as the translational stage is moving. So how do we use it? We use it in reflection mode. So we actually acquire a first spectrum by analyzing the metallic plate without the sample. Then we place the substrate without the metasurface on top in order to characterize the dielectric material. And then we perform we analyze the reflection spectrum when the substrate with the 2D material, in this case the metasurface on top, is placed under the beam. So when we look at the time domain traces, we can actually extract some useful information about the thickness of the material and the average refractive index, because the zeroth order echo, I mean the echo that you get in the time domain from the first reflection gives you the thickness of the material because it doesn't interact with the material. And the first higher order echo, that means the ray that goes through the sample and goes back to the antenna, gives you an idea of the thickness and the refractive index. Since you know the thickness from the specular reflection, you can extract information about the average refractive index. But you cannot know anything more. And usually, materials, especially in the THz range, exhibit a given dispersion, frequency dispersion over the THz spectrum, and you may want to have a precise characterization of this dispersion of the loss tangent and the refraction index in the THz spectrum. To do that, you need to resort to the frequency spectrum, and in order to analyze precisely the spectral reflection coefficient, it is again helpful to have an electromagnetic model. So again, we perform the transmission line based analysis of this configuration, and we obtained in analytical form the theoretical reflection coefficient that can be expressed as a function of the dielectric parameters, as a function of the frequency that you want to characterize of the materials. And you can compare this theoretical model with these free dielectric parameters with the measurements, and you can just fit your theoretical models, these free parameters, to match the measurements. That is, and minimize the error, the Euclidean norm between the measurements and the theoretical reflection coefficients over a given bandwidth. The same approach can be repeated for a sheet reactance, a metasurface, a partially reflecting screen, and even a thick PRS, as we can see. So with metasurfaces is a bit more complicated, but we established a very simple and precise manner to characterize the sheet reactance of these metasurfaces. Basically, when you replace when you derive the reflection coefficient, theoretical reflection coefficient of this kind of structure, by analyzing this expression, you will end by discovering that the reflection minima appear close to the multiples of lambda over 4, as in an ideal Fabry-Perot. And this resonance is, however, when the metasurface is placed on top, shift with respect to the ideal Fabry-Perot resonances backwards or forward with respect to the ideal Fabry-Perot frequencies. In particular, you have that when you have a capacitive sheets that has a negative reactance sign, you have a blue shift of these resonances in amounts that depend on the value of the sheet reactance. When you have an inductive sheet, these resonances red shift with respect to the ideal ones. And again, they shift in amounts that depend on the sheet reactance. So by measuring the shift of these resonances with respect to the ideal Fabry-Perot resonance, you have a very accurate technique to characterize the sheet reactance of a metasurface. And this is actually what we did in simulation. So here you see the dashed lines, black dashed lines represent the Fabry-Perot resonances, and the bluish and reddish curves are obtained by changing the reactance value of a capacitive sheet, that is the patch, or an inductive sheet, that is the strip grating. So we actually realized this structure. Who realized? Well, another magic. So Francesco and Luca did the magic now. So you know, it's again ChatGPT. So we said once, is no need to repeat. So they actually realized these metasurfaces, and we actually measured with the spectroscopic system that I said, and we found an impressive agreement between the theoretical models and the CST simulations and the measurements. So we were able to confirm that we can realize such thin metasurfaces and characterize them at THz with a very high accuracy. We actually realized even a metasurface that is neither a patch or a strip, but is a more complex geometry, the fishnet one that I said. Why? Because as you have seen in one of the first slides, this geometry was quite helpful to obtain a very directive beam from this structure. So we actually characterized the structure in the THz range, and we confirmed that when we realized by photolithography such unit cell, we are able to obtain such a low value of the sheet reactance that in full wave simulation tell us that we can get a very highly directive beam. So this, of course, is a highly directive beam that could be generated in the THz range, assume we are able to realize this feeding scheme with the waveguides, but will never be a large, will never show a large bandwidth because it's a thin metasurface. But again, this would be a record in scientific terms, because still there are no experimental validation of a pencil beam radiated by a THz structure. So even having a validation of a radiation pattern from such kind of structure will represent a big achievement. But we need to do more. We need to do something different because, as I said, we were interested in the thick PRS, not the thin PRS. But in this case, in order to prove the gain bandwidth enhancement phenomenon, we cannot just look at the amplitude reflection spectrum. We need to look at the phase. But fortunately, the spectrometer, as a time domain spectrometer, through the Fourier transform, give us the amplitude and the phase spectrum of the system. So in this case, the problem is that our setup, as it thought, is a closed environment because it has a metallic backplate below, and this is also a condition where the phase is very sensitive to vibrations. So in order to have accurate measurements, we have to remove the backplate from our setup. And actually, in order to evaluate the phase of the reflection coefficient in a thick PRS, in any case, we need an open boundary environment. So we need to analyze the phase and the reflection coefficient, but in an open boundary when the sample is placed and has no metallic backplate on the bottom. How can we do this? Dimitris did the magic now. So he thought this kind of experiment where he drilled a hole basically in a foam that was big enough, was small enough in order to be to allow the sample to stand on the foam, but was small enough to be able to be centered where the metasurface on the sample was placed. So basically, when the sample is bigger of this hole, but the THz beam can impinge on a metasurface on the larger sample that is actually centered on this hole. So the environment is an open boundary because we don't have a metallic backplate below this hole. And we actually, again, there is no ChatGPT, but Francesco and Luca did another magic. So they realized also this kind of metasurfaces. We realized different geometries based on patches and strip gratings. And first we analyzed them in the closed environment, just as a sanity check to see if the phase was a reliable results. So in this case, we analyzed the phase of the reflection coefficient when the metallic backplate was underneath the sample. And even if the literature said that the phase is quite sensitive to vibrations, as you can see, we found an excellent agreement between measurements and the theoretical models. So probably at this frequency is not really an issue, the presence of the metallic backplate. Anyway, we performed this, this analysis has been made both for the patches and the strips, but agreement and results are quite the same. We performed then the analysis of the phase of the thick PRS, and we actually were able to demonstrate the non-Forster behavior of the phase of the reflection coefficient. And then we had the first experimental proof that a thick PRS can enhance a gain bandwidth phenomenon, and a gain bandwidth enlargement in a Febvre cavity leak equivalent antenna device. So this concludes my presentation. I think I was long enough. With respect to my expectation, I don't know yours, so I can skip the conclusion and ask you, did I do the magic? I mean, I was the only one who was missing it. So, thank you. And yeah. Less than the vector network analysis you have, much less. I'm kidding. Yeah, but the time domain spectrometer costs about, with the imaging module included, costs about 100K euros. Another spectrometer that I didn't show in this presentation that is based on the frequency domain spectrometer that is based on the heterodyning of two continuous wave lasers. It costs about 50K euros. Is included in the setup. It's part of the setup. It's not that expensive, yeah. So when we is a very low power. So for the time domain spectrometer, you have just one laser source of milliwatt power. Is about 20 milliwatt power at telecom wavelength, 15 nanometers. And the power that you emit at terahertz is about 70 microwatt. It is very low, but the antenna are extremely sensitive. Even with this very low emitted power, you get a dynamic range of about 70-80 dB. That's quite a lot. Yeah. The point is that when you generate the terahertz with this system, you cannot use it. You can use it to characterize components, devices, but it's not likely that you use it to feed antennas. I mean, for a laboratory experience, you can do it, but on on a for commercial military purposes, for real case scenarios, cannot be used. Yeah. But the idea is that we only use this setup to characterize the structure. The idea is to use the device, the cavity with the metasurfaces, to be used with possibly the waveguide that you are trying to get for the VNA, because it should not be difficult to couple the radiation, say at 100 gigahertz, the W band, say, of your horn to the slot of a cavity like this, and we can simulate that that kind of coupling, and I'm almost sure that we can get a pencil beam from this kind of coupling. The point is how we can measure the radiation pattern, because with the VNA we can get the S21 at first, but if you want the radiation pattern, we need the translational state. We need a 3D axis translational stage, at least to probe the aperture field and then evaluate the radiation pattern through far field, through Fourier transform. So usually at this large frequency, what is done from my experience, not at THz but at 80 gigahertz, say, is that you just feed your antenna with a horn, a waveguide, whatever, and then you probe the aperture field, close to the aperture field, with a 3-axis translational stage, and then you take those complex valued electric field measurements, you do the Fourier transform, you get the radiation pattern. That is, so that would be, I mean, as a receiver, yeah, as a receiver, yeah.
Yeah, I see. I this well, just the question, but the hypothesis, the essentially is modes and
Between two plates, yeah. Yeah.
Yeah, but again, what I found interesting is that you really understands all the process.
Yeah, I was born as a theoretical guy, and I have been forced to be an experimental guy. So in order to do less efforts as possible with the experimental part, I had to figure out how to model the experiment.
Of course.
Yeah. Because one possibility would be to change the setup, the experimental setup, to do measurements in a different way, but that was too much for me. So.
No, but this is a good point.
Yeah.
Have something we can try to find different
Overlaps, you mean, connections.
different structure.
Mm-hmm.
So far, you are giving let's say, very behavior structure.
Mm-hmm. Mm-hmm. Yeah, okay.
I don't know if you have the TL recognition line method works quite well with these structures, but they are more or less
Non-aligned, disaligned, misaligned.
they follow, Cartesian
Okay.
shapes.
Okay.
So it helps the recognition line. But the shape is arbitrary shape. They have some
The unit cell of a metasurface can be arbitrary, more or less. So we can,
arbitrary.
yeah, that
Yes, it's a
the-
matter of finding
That is the point. Yeah, as far as you deal with planar structure, even if you have multiple layers, I mean, here I have considered just the electric layer with the metasurface on top, and for the metasurface only the sheet impedance matters, as you said. But the model that we have deals with anisotropic dielectric layers, even magnetic layers, and can also be extended to multiple layers and multiple interfaces. So you can analyze structures that are made up of to n layers and interfaces with anisotropic layers. So that is a, but you still have to think about a structure that is stacked, so is invariant with respect to the a stack of planes. Yeah. Of course, you can. We should start from zero in the sense that we cannot use the model that we have, but you can also you have a transmission line theory for cylindrical reference frame. So if you want to study coatings on conformal surfaces, in principle you can do that. You have to change the the basis functions of the transmission line model. You no longer have cosine and sine. You have the Bessel and Hankel functions for cylindrical transmission lines. Multiple layers, yeah. Yeah, more resonance. Yeah. Yeah. Yeah, the point is that as far as I have seen, you always reach a boundary. I mean, you even if you up to 3-4 layers, maybe you can still find a benefit in increasing the bandwidth. But up to a given point, you are left with a large bandwidth and probably a poor directivity. I mean, you can, yeah, that's the point. It's always, yeah. Yeah. No, actually, we found that there is. Yeah. 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 I mean, that is the reason why yesterday I asked Cynthia a few more details about the sources, waveguide sources that you are buying, because if we have details about these feeders, we can try to figure out how we can couple radiation from the feeders to such kind of structure. And at least we can maybe we can not have the radiation pattern, we can have the S parameter at first, then we can move step by step in that direction. Yeah, the cross validation between this. Yeah, sure. Yeah. Yeah.
leakage that and noise and all the
Okay.
things you have in the calibration center.
Yeah.
But in relation to the radiation method, I believe, I don't know, I never tried, I only read about, if you have a kind of compact range,
Yeah.
that we have, and it's like, it's a parallelepiped,
Yeah.
the caption very small, then you have a reflector in the side, and this, you can illuminate this reflector with a waveguide linked to the DNA.
Okay.
Then you have this here, left to see part one here.
Yeah.
Then you illuminate the reflector.
Yeah.
Then it comes in this direction. And here you have the positioner and the
Yeah.
Metasurface.
Yeah.
Let's to see the simple.
Yeah.
Metasurface. Here is the feeder,
Yeah.
reflector. Then this is the Metasurface.
Yeah.
You can use in near field. You can correct the size of the apertures. You can translate the measure in near field and translate to far field and have the surface. The material is your structure. I don't like
Yeah.
as Metasurface, but you can have your structured method.
Yeah.
And try to form the radiation method. We have structures up to 300 gigahertz already in the way.
Yeah. That is no. It's possible. The point. Yeah. It's possible, and there are the point is that at 300 gigahertz you have a lot of metasurface that was as reflecting metasurface that use radiation from an external source. But this is something that you want to avoid usually because you have an external source that makes the structure bulky. And you, on the other hand, want to have a feeder that is integrated with the antenna. That is the reason why we study these sort of transmissive metasurfaces, because you want to avoid the external feeder with the big reflector because it is not very practical. And this is, and also is something that is widely investigated in the literature. So on the other hand, this is quite novel and there are very few realizations because it's more attractive because it's more compact, because your waveguide feed is integrated with the antenna, so you and you can already there.
How to do this function, this shape.
Yeah, we did. Yeah, I mean we. Yeah, yeah, we did it. This is. I mean, I don't have the picture. Probably we have it in a previous presentation of Eduardo, but this is actually what we did at 86 gigahertz. So basically we have the photoconductive antenna, this guy here, yeah, that radiates a beam in front of a standard horn. That is no standard, it is a circular horn waveguide that is attached to the, here in yeah. No, but these are not the. I mean, they are not scaled. These pictures. Yeah. So we can match the slot to have the same dimension of the waveguide. Yeah. Yeah. Or yeah, or otherwise you can directly use the you can use a free space coupling. You don't need you can get rid of the waveguide if you think they can position. So probably the coupling efficiency will not be as good as this one.
If you have this PCA side and harder than this lens, and then
Yeah,
space,
yeah.
and then you have the corrective position of the
Yeah.
exactly
Yeah.
the size of the waveguide.
Yeah.
Then you have the
Yeah,
pattern
that was.
it's a delicate setup, but that's
I mean, is not so delicate because I mean it depends the frequency that we pick. But if we scale down the design for having a first proof of concept at 100 gigahertz, it's not really any. I mean, with Eduardo we calibrated by hand the antennas at 300 gigahertz, 1 terahertz. So it's difficult. I mean, but you can still do it. You can still do it because what you can control 1 millimeter by hand. It's not easy, but you can do it. So, and yeah, yeah, yeah. But 1 millimeter, you need it at 1 terahertz probably. When at 300 gigahertz, if we scale down to 100 gigahertz, half a centimeter tolerance is. Yeah. For instance, the focus of the waveguide horn that we were checking yesterday was 1 centimeter. So 1 centimeter is feasible. Yeah. So 1 centimeter for spot size. So 1 centimeter is feasible.
1 centimeter is this size. It's good.
Yeah, yeah.
But we need to decrease the frequency.
Yeah, yeah, sure. Sure.
Go closer to 75.
But the point is that we did it at 300 gigahertz because our setup cannot do
Yes,
that.
I know.
Yeah.
To make a difference. But we can also buy. Yeah, we can buy a focus lens with the 100 gigahertz, and then you can see.
Yeah. Information. Yeah. 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 No, a big impact. Yeah, we. Yeah, I did it in RAM with spline tools in W band. So we did it 75 from 75 to 110 gigahertz, and we managed to send on-off key signals up to 1 gigabit per second, and was a very nice. Yeah. Yeah.
And also we can make connected to our optical
Yeah.
so we have another lab.
Okay.
It's an optical communication. So here we connect this.
Yeah.
Make something like terahertz of over
Fiber. Okay. Yeah. Nature electronics. Photonics. Yeah. Romeo should be here to hear that. Yeah. You can steer with frequency with this structure. If you change the frequency, you don't actually steer. You get a conical beam. So from a pencil beam, you get a conical beam, like the. unfolds as a conical beam, and this is useful for automotive because they need conical beam with omnidirectional feature. But you cannot actually stick the pencil beam in an arbitrary direction like in pista array. In that case, you need to feed you need more feeders with a single source, unless you use a tunable metasurface that change the phase somehow. But that is quite complicated. At these frequencies, I never seen something like that. Yeah. Yeah. Waves. With this structure, you can have it. You can have a Bessel beam, but for this structure you have two ways to generate a Bessel beam from this structure. For instance, you have to truncate the structure with actually you have a cylindrical resonator basically. The antennas that we are thinking of here are supposed to be electrically large, so and with say free space at the end. So you have say an electric slab that is grounded with a metasurface on top, and is about 20 lambda diameter, say 20-30 lambda diameter. If you wanted to create a Bessel beam from this structure, apart from studying the metasurface in a different way, you need to truncate the structure about 2-3 lambda with a metallic circular metallic rim. In that case, you can have a Bessel beam. It will be a very narrow band beam, and but you can do, actually we did it in the E-band, 77-86 gigahertz, with sort of similar device. In that case, we didn't have actually a metasurface, but we had an annular strip grating on top. So we had annular strips on top of the structure, and it worked as a periodic antenna. So the physical behavior was a bit different, but worked for radiating a Bessel beam. The point is that if you want to do communications, Bessel beam. If you want to do, say, indoor short-range communication and you want to target certain distances of ranges of meters, at these frequencies with a Bessel beam you cannot cover it, because you can get a Bessel beam only up to the non-diffractive range that is always in the Fresnel region of the antenna. It rarely exceeds the Fresnel distance. So, and the Fresnel distance for such kind of structures at such large frequencies is less than a meter. So, localized waves are useful from my perspective, for applications that require focusing, like imaging, diagnosis, sensing. Not that much for long-range communication. For short communication, for near-field communications, for sure. That is the reason why for this project we prefer to think about directed beams in the far field rather than localized waves. The point is how you want to generate a Bessel beam. If you want to use a lens, it's quite easy. For instance, at AESS they already sell the Solupiga lenses, the IPS. They don't cost a lot, and they convert a plane wave into Bessel beam. It is quite common. if you want to do a sub with a planar structure as this one, and you want to achieve a large distance, you have to go close to the cutoff of the leaking modes of the structure. So this poses challenges. So you have to resort to other antennas that heal the long-standing problem of the open stop band of the structure. This is something we have worked with Eduardo and Professor Enrica Martini insieme, University insieme. It's something we have investigated. We still don't have experimental validation. It's something we are doing. We are in the process of doing, but at lower frequencies. Because again, such high frequencies is more challenging.
Think about the curve of this structure, so like this conformal, isn't it? Okay. Just think about this to help you in case you can.
No, because if you bend the structure, you spoil the radiation. So it's, even there are also studies on, because when you have such kind of heterostructure, the point is that you have to ensure a resonance along the plane. So when you bend the structure, you lose this resonance mechanism, and is rarely beneficial. I never tried, but I don't expect needing.
If you have some much benefit because
Yeah.
you change the structure.
Yeah.
As a best thinker, waveguide bands.
Yeah.
They need to be formless as it's complicated.
Yeah.
Yeah,
It's another.
it's another way.
Yeah. 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 I think that was something we were trying to study with Rafaela last year with the spiral antenna, the conformal design. I remember we.
Yeah, we were still but it looks like it works better because the reflector rate is staying.
Yeah.
Not much. We still need to verify.
Yeah.
Well, okay. Okay, well, thank you very much. Well,
Thank you, Hugo.